Hello and welcome to today's webcast brought to you by Lightwave. Today's event, Fiber Characterization Part 2, will be presented by myself, Larry Johnson of the Light Brigade, and Tim Yount of Fiber Insight, with the majority. Tim's going to take over. The event's also sponsored by basically the fiber industry, and we want to make sure that we present the best we can for everybody. And so we really want to review a couple items before we start, but the others to request questions as we cover different content. So before we begin, we wanted to cover a few housekeeping items. You can expand the slide area by clicking on the maximize icon on the top right of the slide area, or by dragging the bottom right corner to enlarge. In fact, you can expand and reposition many of the components on your screen, so feel free to arrange as you desire for your best viewing experience. At the bottom of the audience console, there are also multiple application widgets you can use. And if you have any questions during the webcast, you can click the Q&A widget and submit your question. However, we're going to be answering most of the questions, if not all of them, at the end of the session, just because there's a fair amount of slides. We have 32 total slides, of which about 7 of them are introductory or closing, and that's about 25 slides in the body itself. And that if you experience any technical difficulty during the webcast, please click on the Help widget, and it has a question mark icon and addresses common technical issues. If you still need assistance, just type your issue into the Q&A widget, and a member of the webcast team will work with you to correct the problem. Any additional resources for this webcast can be downloaded via the Resource List widget that looks like a green folder at the bottom of your screen. So for your convenience, the presentation will be available after the session. We will be sending a link to you, or a content for it to say how to access the PDF for it. So it won't be presented live, but we will get it to you afterward. The other one is, as we found in our last session, which is archived by lightwaveonline.com, which is Fiber Characterization Part 1. If you did not participate in that and you wish to, it's accessible via, again, lightwaveonline.com for your viewing as well. We hope you're able to take part of it. This one is the add-on to it, which really goes into more depth than the initial one was, which was more introductory levels. And we will send you an email message, and of course you can also access it via the Lightwave Online. Okay, so a little introduction on Light Brigade and Fiber Insight. So I don't believe I need to read all this off to you. I believe you can see it as well. One bullet that's probably missing is a listing of our Fiber Characterization course. And at this point, I'm going to turn it to Tim Yount, and he's going to provide the introduction to Fiber Insight education and training, as well as start the formal program.
Hi everybody. Thanks, Larry. I'm Tim Yount with Fiber Insight. Again, you can just read this slide. We're basically a training company and also training in the consulting. One of the areas that we specialize in is providing certification program training through OTT, or Optical Technology Training, where we have both a Fiber Characterization Advanced Certification Program, as well as an Optical Design Program called CONA. CFC is the Fiber Characterization Program, and in addition to Advanced Test Consulting. So we're pleased to be here and have the opportunity here to talk about Fiber Characterization today. It just so happens that I happen to be in Kansas right now, and we're at the midpoint of a Fiber Characterization course, a CFCE course, that I'm actually teaching here in Kansas as we speak. And a lot of my students are actually in here observing the webinar as we proceed through it. So a little review from the last, we had the webinar back on December 1, talking about the basics of Fiber Characterization. What is it? And what are the basic tests? So I wanted to review a little bit about that very quickly. So one of the big questions comes up is, what is Fiber Characterization? There's a lot of different people feel like some people think it's just loss in ORL and OTDR. Other people think it's dispersion and CD and PMD testing. It's actually whatever. It depends on what your network is. And so we have a lot of different networks of different types. You know, so you define the fiber characterization requirements based on the application, the type of network that you're dealing with, enterprise, fiber to the X, it could be a DWDM network, just a simple point-to-point, or even a CWDM network. So what exactly is required to qualify those networks to make them work properly? It can also be tied, in terms of what tests you perform, is also dependent upon the speeds, the data rates, whether it's lower speed networks or whether it's 10 gig or higher networks. So we're going to talk about all that. And again, we reviewed last time, you know, when we get into network challenges, high-speed networks and the challenges they provide. So when we get into DWDM, where our channel spacing is really tight and our data rates are higher, these challenges also challenge our basic testing requirements. So higher data rates are more sensitive to noise. They're more sensitive to reflections. So you know, even our basic tests become more critical in terms of the accuracy of how we do those. And you know, link loss is an issue in all networks, and so we have to start with that baseline of the fundamental tests that we need to perform. So let's review these basic tests once more. And again, this is what we covered before in the previous webinar. The basic testing, you see them listed here. When we talk about the connector inspection and cleaning, this is something you do no matter what you're doing. It doesn't matter. This is fundamentals. This is what you would do anytime you're going to touch a connector. It's always a matter of inspecting, and if it's dirty, you clean it. If it's not, don't clean it. Just plug it in once you check the other side. And remember, there's not a loss through a connector. It's always a pair. So you're always dealing with two connectors that are mated together, so you have to make sure both of those are inspected and clean. And that's not just the connections on your network, that's also the connections on your test interfaces and any patch cords or access test cords that you're using to get into the network. In terms of optical insertion loss, you know, we're talking there a simple test in dB. It's a loss between the start and the end of the link. And this is typically, to get the most accurate measurements, these are actually performed bidirectionally and actually looking at the average loss in both directions. In the case of optical return loss, that's how much energy is reflected back from the network. You're only concerned about how efficient the light gets through the network, which you're also concerned about how much light's reflected back. We don't like reflections, so we try to minimize those. And we actually perform these, the most accurate ways to perform A to B and B to A. You can actually have a fail in one direction and have a pass in the other direction. In terms of OTDR testing, that's another very basic. I mean, the OTDR I refer to it as the Swiss Army knife of testers. It does so many different things. It's probably the most, overall, the most flexible and valuable test tool that you have overall, because it can do all of these different things: length, attenuation, event loss, event reflectance. It'll even perform ORL testing. Or span sectional testing. So, and this is also the only tool that provides you with a visual image of the link in terms of the ability to troubleshoot, the ability to isolate problems. If you have a fail in loss or ORL, the OTDR actually allows you to isolate where that problem is and pinpoint it and get someone on site. Okay, so these are all fundamental tests, and they're done in any network, whether it's low speed, high speed. These are all very important across the board. So, how critical are the basic tests in the high-speed networks? I think I mentioned this before. They're even more important with high-speed networks. Okay, so we've got to make sure we take care in those fundamental tests. So now let's talk about tests required specifically for high-speed networks. So if we consider those tests to be the baselines, when we get to 10 gigabits per second and higher in DWDM networks, we then look to add tests to those fundamental tests. So this is all the basic tests plus fundamentally CD or chromatic dispersion and polarization mode dispersion. We're also going to talk about spectral attenuation. That's kind of an optional test depending on what your application is. It's not required in DWDM in all cases, but it's also useful. So we're going to talk about those three in more detail here. So first, let's talk about chromatic dispersion, or CD. First of all, what is it? So what we have here is chromatic or color dispersion, where when we send pulses of light out, or data pulses of light, and we're transmitting multiple wavelengths in this pulse, these wavelengths spread out because light travels different speeds over different wavelengths. So the pulse actually spreads out. With positive dispersion, your longer wavelengths travel slower and your shorter wavelengths travel faster. So these pulses spread out over distance. Here's an example of what this looks like. So let's say your transmit pulse they're all bunched together here nice and tight, like you see in this one picture, the first picture. And then as you go down the length and you get to the far end, these pulses have spread out and they're further apart. What you don't want to have is pulses overlapping. So in lower data rates, you're pretty much okay here, where you see the lower data rates spreading out, and they're not really overlapping. But when you get into higher speed networks like 10 gigabit and higher, these pulses will actually spread out and start to overlap each other, and this will cause data errors in this case, and that's a problem. So for CD, in terms of chromatic dispersion, to be more specific in terms of the limits that CD has, it's how far can you go before you have to do something. In the case of chromatic dispersion, you can actually compensate. We have these devices called CD compensation modules, or CD compensators. And there are various types of these. I'm not going to get into the details on those, but they can actually allow you to adjust the chromatic dispersion to bring it back in spec. So if you look at these data rates, you can see the amount of tolerance in that second column. So here the first column is the data rate or the baud rate. I'll explain that a little bit later. Or that could be the bit rate or the baud rate, depending on what you're dealing with here. The CD tolerance, and this is the value of CD, or the total CD allowed in picoseconds per nanometer, in the second column. And so as you can see, the tolerance level drops dramatically as you increase speed. So in a 10 gigabit per second SDH or OC192 network, you can tolerate about 1,000, where with 10 gigabit Ethernet, it's actually more stringent, and it's much more stringent at 40 gigabit per second, or OC768. So that translates then, you could translate that into based on types of fiber. And here are the examples we're using. In the third column is G652 fiber. Okay, this is your more typical all-purpose fiber, and we're referencing these at all at 1550. So you can see the distance range that this will tolerate approximately. These are typical numbers. The distance range before that signal has to be compensated for to bring it back within specification. These are maximum distance ranges. And the last column is actually the typical numbers for G655 fiber, which is fiber that's non-zero dispersion shifted, which is optimized to operate in the C and the L bands. And you can see the distance ranges those are, because the dispersion at 1550 is much, much lower than it is at 1625. But in fact, these numbers can vary because each network vendor has different tolerance levels for their particular electronics, and so you really need to check with your vendor to see what's specific. The other topic here is baud rate versus bit rate, and this is in the case especially of line side versus client side networks, where let's say a 40 gig client side network is actually not true 40 gigs. It's actually either it's usually 10 gigabit per second parallel channels, where you would actually be testing to the 10 gig, because that's actually what's traveling over the fiber. In a 100 gig environment, you would either have 425 gig channels, gigabit per second channels, or you would have 10 gigabit per channel, gigabits per second channels, excuse me, to make up the 100 gigs. So you would actually be testing to the baud rate, or that lower level rate that makes up each of the individual parallel channels, versus the total rate, where in the case of a line side network, 40 gig is actually 40 gig, okay, for example. So when we're looking to, the other thing about CD is not only does it define the amount of chromatic dispersion that your system can tolerate before it's compensated for, one of the great things about CD measurements is that they can actually define the fiber type. So we have what's called a CD coefficient, and that is how much dispersion or CD, chromatic dispersion, occurs in picoseconds per nanometer over each kilometer, and that's called the coefficient. And here you see this typical coefficient curve for G652 and G655. So we know that G652 is zero dispersion at around 1300 nanometers or 1310 nanometers, where it has higher dispersion up at 1550, around 17 picoseconds per nanometer dot kilometer or per kilometer, where G655 is optimized for operation at 1550. So it has actually shifted. It's actually got a shifted curve, which makes it more optimized at a different wave at the 1550 wavelength. So by testing CD, you can also define the fiber type that's in your network. So it helps you in case you're leasing fibers, or if you're purchasing fibers or bartering fibers, or it's fibers that you're not sure about, you can test it and actually find out what type of fiber or classification of fiber it is, and actually what the dispersion level is. And this also helps your engineers plan for how much compensation they need to make in that fiber given the coefficient that it has. This is a little complicated, and again, we can go into that a lot more detail, but not on today's webinar. One example I'll use is the phase shift method for measuring chromatic dispersion. In this case, it's a two-ended test. You're actually going to use a CD receiver, which is actually based on a spectrum analyzer, an optical spectrum analyzer, and then you're going to use a broadband test source, which is like a giant headlight that covers a wide spectrum over either the OESCL band or the SCNL band. So it can be either the band up at the top near the DWDM channels, or if you're doing CWDM, it could actually cover a much broader spectrum depending on the broadband source that you're using. So first you have to reference, and then you actually split those connectors apart, plug them into your optical distribution or your fiber distribution frame, which is FDF here, at the ends, and you're actually going to be able to test it. And that test only takes about 20 seconds with using the phase shift method. So it's pretty easy to make this measurement once you're set up for it. Okay, just to kind of overview chromatic dispersion. One, it's a direction, and it's a one-directional test. Remember we were talking before about the fact that insertion loss, ORL, and OTDR are ideally bidirectional tests. Well, CD and PMD are not. They're only they only have to be tested in one direction. And also, we're interested in determining the overall CD value or the overall dispersion, so we know how much compensation is going to be needed, and that's your picoseconds per nanometer. Okay. And also, we can define the fiber type using the CD measurement by determining the coefficient. And all that information is very valuable when you're designing networks, and when you're going to do acceptance testing or qualify networks, and you're trying to figure out what's wrong. The other thing about the phase shift method, there are several phase shift methods, but the phase shift type methods actually not only enable you to test spans, but they also allow you to test through amplified networks, because you can even use these for ultra long haul or even subsea networks. You can use phase shift methods for that. So some of you on the phone are probably thinking, okay, so what about 100 gig networks? We haven't really talked about that, these coherent networks. Is it still needed? A lot of people say, oh, CD or PMD is not needed for those. We'll talk about it a little bit later, so I'm not going to leave you guys hanging, but we're going to talk about PMD first. So now let's talk about polarization mode dispersion, or PMD. What is it? So this is also about pulse spreading, but in this case, it's a little bit different. Polarization mode dispersion literally is caused by the fact that fiber is not exactly round. Okay, if you look at an optical fiber, and you look at the shape of it, it's not perfectly round. It's a little oval. So that means you've got one axis is wider than the other, if you will, microscopically speaking. So you have your transmission. Your light is transmitting down the fiber in different polarization states. Here we have a slow axis and a fast axis. So as we look at fiber, it's caused by the ovality of that fiber that creates these polarization changes in the fiber as these pulses travel through. So different polarization states or SO states of polarization, which is SOP, travel different speeds. There's a slow axis and a fast axis. So as this light travels down the fiber and goes around curves and is affected by the ovality changes, or external stresses like wind blowing or vibrations or whatever, these polarization states constantly change. And so this is caused by the pulses spreading over the length of the fiber due to the speed changes between these polarization states. Here's a couple graphics that kind of show what try to show what we're talking about. So if the pulses here, if you look at the lower left-hand side of this thing, you see that these pulses are nice and grouped together in different polarization states. So if you thought about one polarization state in vertically and then the other polarization state horizontally, as these travel down the fiber, they spread out, the slower versus the faster ones, and they end up at the other end, and the pulses are spread out due to the polarization states, due to the signal in those different polarization states as they move around. These are constantly changing all over, so the signal that's in one state will switch to the other state and back to the other state. So this happens constantly. The difference in those, or the spacing between these states, is actually called differential group delay. And it's very hard to measure by differential group delay. So what we actually measure with polarization mode dispersion is we actually take the average of DGD over a lot of conditions, and that value is PMD, or polarization mode dispersion. And you can also see in the lower right-hand corner kind of a different way to look at it, showing those axis changes along the way, and the slow and the fast axis. In terms of the test results that you see when you shoot a PMD, a very typical graphical representation is shown here, which is the fast Fourier transform display, or FFT. So here you see the data. The green line is sort of the DGD data that's collected over the delay versus the calculated PMD Gaussian curve fit that you see sort of in the orange color there. Okay, and when you actually look at that data, if you have distance information on the length of that, again, the coefficient, this whole the PMD coefficient is the delay in picoseconds normalized to square root kilometer. So you get both. With the distance, you get the coefficient over the distance, and then the total PMD is just the total picosecond delay based on that averaging those DGD values that you get. And so those are the two values you get by shooting the coefficient and the total, or by shooting the fiber, you get those two values. And in terms of guidelines or limits, here we see 10 gig SONET on the top line, 10 gig Ethernet in the second line, 40 gig, and then 100 gig with Coherent. Now 100 gig we're referring to is basically polarization multiplexed transmission with coherent receivers, and also using DSP, which is digital, the digital compensation, or the digital processing, signal processing that happens at the receive side. And this actually provides very high tolerances of both CD and PMD. I don't think I mentioned it on the CD slide, but so you can see here the PMD limits here: 10 picoseconds at 10 gig SONET, 5 10 gig Ethernet, 2.5 at 40 gig, the limits, and 100 gig Coherent is actually 24, so you can see it's much higher. It's actually, on average, it's about 4 times more tolerant on 100 gig systems than it is in these other systems. And it's very limited in some of these. And look at the distance limits that you can have based on the different dispersion values. So older fiber, basically older fiber, are typically, some of the really old fiber that's in the ground has more of a value of around 0.5 picoseconds per square root kilometer. So you can actually calculate or estimate your PMD by knowing the distance and applying this 0.5 picosecond value, and you can kind of see what the PMD will be for that particular fiber. So that's the older fibers, and so you can kind of look and see typically what the distance ranges are for those. These are absolute limits, by the way. You can't compensate for PMD on direct detection networks, which are the first 3. However, the compensation occurs at the 100 gig coherent level. So with compensation, typically you're going to be able to go a lot further, as you can see there in the fourth line and the third column. With newer fibers, and typically it's even better than this, we're talking about a 0.2 picosecond per square root kilometer coefficient that the newer fibers actually exhibit, and a lot of these actually are well below 0.1. And in actual practice that we test today. But as you can see, the lengths are quite a bit longer in terms of tolerating PMD with this much lower value or better value. So these are the limits that can help you actually plan, design, and know what your limits are going to be depending on what your speeds are. Okay, and there's just 2.2 picoseconds. Effectively, the 2.2 picosecond fiber is rounder. It's much rounder, more truer, and therefore it's going to perform better. Another point just to make here, this isn't something you would necessarily need to remember, but the way PMD limits are defined, it's 10% of the bit period, or in the case of you can see the example here, 100 picosecond bit period is 10 picoseconds in terms of your PMD limit. In terms of testing PMD, and this example is using the fixed analyzer method of doing it, and this is a method that actually does not require reference. So you just attach the PMD receiver and the broadband source to the fiber distribution frame ports at each end, and you turn on your broadband source, you set it for PMD, and then you run the test. And you get those numbers, plus you get that Gaussian curve. So PMD, again, a unidirectional test. You're looking at the total PMD value in picoseconds, and that will help you define the limit in whatever speed you're operating on and determine whether your fiber is going to be able to operate on the length that you're trying to do, or it tells you what the length limit will be for your particular network. The thing about PMD, though, is the PMD, where CD is a fixed number and it never changes, and it's inherent to the fiber that you're measuring, PMD can change. So it changes over external conditions. Fiber under stress will change. So it'll go up and down a little bit. So actually measuring PMD over different conditions is always a very valuable thing to do. You might want to make a measurement when it's the coldest day of the year, when it's the hottest day of the year, when it's windy days, if you have a lot of aerial cable. Under different conditions, and you can actually see the sort of the distribution of PMD under these different conditions and how it's going to behave in your network or on the fiber that you have. Again, you also get the PMD coefficient, and there you can kind of more of a planning tool, and it can also indicate when, or give you some more information between the total PMD value and the coefficient of when you have bad PMD fiber. So if you're really looking at old fiber, you might want to avoid very old fiber because it could have very bad PMD. And so this allows you to identify the fibers that have poor PMD versus those that have good PMD. So all these, the measurements are very valuable. The fixed analyzer and the general interferometric methods. We didn't talk about the general interferometric method, which is also termed as GINTY, G-I-N-T-Y. Both of those methods actually also allow you to test through amplified networks. There are other methods for both CD and PMD that do not allow testing through amplified networks. So know based on the method that you're using what the capabilities of that particular test method provides you, and what the capabilities are, the trade-offs, and the limits. Okay, so 100 gig network discussion a little bit more later. First, we're going to talk a little bit about spectral attenuation. What is it? A lot of you may be very familiar with this kind of a trace. This is called different terms. Spectral attenuation could be an attenuation profile curve, or some people actually call it a water peak curve. And so what this is doing is, on the left-hand side, the vertical scale here, this is measuring attenuation in dB per kilometer, okay, looking at the attenuation of a fiber. And across the bottom is wavelength. So this actually, the spectral attenuation is a lot like insertion loss, except instead of just measuring it at certain wavelengths like 1310, 1550, or 1625 that insertion loss is measured, spectral attenuation actually allows you to plot the loss over a range of wavelengths. Or it's basically loss as a function of wavelength. So it actually allows you to plot the performance over a wide range of wavelengths. So if you're doing DWDM or CWDM, it allows you, depending on the broadband source you're using, it allows you to plot all those and look at the performance at each one. It's also a great cross-correlation if you're doing acceptance testing for insertion loss using IL and also your OTDR. It's another cross-correlation tool. Are the numbers, are your loss numbers matching up closely with the IL numbers that you ran that you also tested? So in my classes, we go over a lot of things like looking at, once we do all the tests, we go back and we correlate those and see if they're close, see if they're representative, because it provides a lot of more validity. It lets you know that your tests are valid. It just helps confirm that. In terms of CWDM, we deal with these water peaks down at the 1383 water peak, which you see at around this one where you see the little red line is lower than the black line. The black line indicates older fiber that had higher water peaks, and then more modern fiber or low water peak fiber, we've eliminated a lot of those water peaks, and so therefore you can transmit now with, for instance, CWDM over these wavelengths that you didn't used to be able to, because the loss was too high in those particular wavelength areas. So now that the low water peak fiber, CWDM is possible over a very wide range of wavelengths where it wasn't before. However, this requires a special broadband source if you're using the methods based on the spectrum analyzer to actually that are actually providing a light stimulus at those lower wavelengths. Otherwise, the test would be performed with SCNL band, which would be more of a DWDM type of application. So be aware of what test capability you have versus what types of applications you're going to be performing. Measurement process, it's kind of like insertion loss. You're going to do a reference, a loss reference, and then you're going to hook it up and test it through the fiber distribution frames, the same as you do all these other ones. And you just make sure your broadband source is set for spectral attenuation or attenuation profile, same thing, and then you run the test. And within that test, you will get both a dB value, and you'll get a dB per kilometer value if you actually provide the distance into the software as well. Okay, so total loss value, loss coefficient, dB per kilometer, over wavelength in both cases. This test also will provide you the ability to, where you can't test through amplifiers with a standard loss test. It has to be span by span. With spectral attenuation, you can also test through amplified networks. So this is actually one of the benefits of the attenuation profile of spectral attenuation. It's a very useful tool for CWDM networks when you use this wider band broadband source. However, this is not one of the required measurements. This is more it's an optional measurement that is not considered part of the critical fiber characterization measurements, but it is a very useful tool. So we go back to this topic that we alluded to before. Is CD or PMD tested needed with 100 gigabits per second coherent networks? And you can also ask the same question about higher speed networks than 100 gig, 400 gig, or whatever. So there's a lot of debate that's been going on. People say, well, since the electronic compensation in the DSP or the digital signal processors of the coherent network and the coherent receiver can compensate for CD and PMD, that there's no reason to test it any longer. You don't have to test the fiber any longer. And it depends. The answer is it depends, but usually you do need to measure, or it is recommended that you do PMD and CD measurements as well. You have to do all the other ones, but in terms of CD and PMD, it is recommended that you test these, even if you're doing 100 gigabits per second. And the reason is this. Ask yourself this. When you're installing cable and you're putting it in place, and you're going to be running 100 gig, is that the only speed, 100 gig or higher, with Coherent that you're going to be using on that cable? And the fact of the matter is, in most cases, companies change. They change what they're doing with the fiber. They may use certain fibers in the cable for certain speeds and others for other speeds. So if you know that you're only going to carry transmission with coherent detection and digital signal processing on that fiber, okay, fine. Tag those fibers and don't worry about CD. You can also worry about, or you can also say that about PMD, but remember, PMD is not relatively unlimited with 100 gig. It's 4 times more tolerant, but there is some limits there as well. But if you don't know for sure what you're going to do with that fiber, you really need to consider baselining it. So what we're saying here is what you can do in a given cable. When you have, let's say, 48 fibers of cable, you can have different fibers, of course, carrying different speeds. So you might have 100 gig on some, you might have 10 gig on some, 40 gig on some. But also, you can actually carry multiple speeds on the same piece of glass over different wavelengths. So you might have one set of wavelengths in one area that's carrying 100 gigabit per second coherent. But you could also have multiplex on the same piece of glass, 40 gig or 10 gig at different locations. So the fiber is so flexible, it allows a lot of flexibility in what you're doing. But if you are going to be using, or you think you might be using that fiber for anything else, you really need to baseline. So the recommendation is baselining all your fibers, and tagging for operation at qualified speeds is one approach. It's not, but the thing is, it's not only good practice, it's smart infrastructure management, because things change, people change what they're planning to do, people purchase fiber, sell fiber, trade fiber, lease fiber, and they change their infrastructure. They move their infrastructure around. So having a good visual picture or a good baseline of the fiber performance across the board is just good common sense management practice. So networks evolve, they get reconfigured, rerouted. Do you know what you're going to be doing 2, 5, 10 years from now? So in summary, fiber characterization, the definition depends on what you're planning to do with the fiber. So the definition changes depending on what my application for that fiber, the speeds I'm going to be carrying. But I need to characterize my fiber no matter what. It just depends on what tests I'm going to perform that properly characterize the fiber for what I'm going to use it for. The basic tests, you want to do those always. So especially for lower data rates and shorter links, and these tests here, inspection, insertion loss, return loss, and OTDR. Those tests apply across the board. So you want to do all of those tests, plus you want to do the advanced tests for DWDM networks and higher data rates. And the demarcation point here is 10 gigabits per second and higher. And that's adding the CD and PMD as a minimum, and also possibly the spectral attenuation. But be smart. Baseline it following the 10 gigabit per second demarcation rule. And if you're going to be transmitting 10 gig or higher, test it across the board with all of those things, including the advanced stuff. So to just let everyone know, I don't know if Larry wants to talk about the fiber characterization fundamentals, but we do have classes coming up in 2017. Light Brigade delivers the fiber characterization fundamental 2-day class, and here are the dates that are happening and where they're going to happen. We're also now offering CFC classes through Light Brigade that we at Fiber Insight deliver, and we actually have three classes for CFC scheduled for this year, as well as 3 classes for KONA, the design class, scheduled throughout the year. But you can look here and see what the dates are as we go forward. Now I'll turn it back over to Larry.
Thanks, Tim. That was very enlightening. And we do have a fair amount of questions. I also want to just put a little comment in on the upcoming courses that we also provide customization of any of these courses for clients worldwide as well. So don't feel that you're limited to just these locations and these dates. I also want to put a little plug in for the upcoming Optical Fiber Conference, where we're going to be showing and discussing PMD and CD and fiber characterization at the Light Brigade booth as well. But I want to get to the questions right now, so give me 1 second just to hit the right button here. And Tim, I'll address these to you. I'm going to, because the questions come in inverted, I'm going to go to the oldest ones first. And so one question, do you know of a method to determine what fiber types are on a mixed fiber span?
That's a great question. So so mixed fiber types. So when you do a CD test, you're going to see the total CD value, and then you're going to see the coefficient. If it's a mixed fiber type, you will see a number, a coefficient number that's going to be somewhere in between. So let's say it was a mixture of G655 fiber, which might be 4 picoseconds per nanometer dot kilometer or per kilometer versus a G652 fiber, which would be around 17 picoseconds. So if you see something that looks like it may be 12 or 11, it could be a mix. It's probably a mix between two fiber types. The really cool thing about all the different tests that you perform is some of the tests that you perform can help other tests to clarify what's going on. So if you look at the CD result and then you also look at the OTDR result, if you have mixed fiber types, it will show up on the OTDR as gainers, as apparent gainers between, basically it'll show a fiber, dissimilar fiber transition. So in one direction you'll have a gain. So for instance, if I go from G652 fiber to G655 fiber on my link, it'll actually show an apparent gain when I shift to that. If it's a section that's spliced in that's 55, after that section is done, it'll drop back down again. Or it could just be, we were talking about this today in class, it could just be a shift. So let's say I hand off, I've got a fiber link and I'm handing off to another carrier or maybe somebody I bought fiber from, and the rest of the link is G655 where my section is G652. And we see, so you'll see a gain in one direction, but if you shoot from the other direction back, you'll see a loss that's greater than the gain. So we can use the OTDR and the chromatic dispersion to clarify if we get the coefficient results that look a little strange, we can then correlate that with the OTDR results that we're seeing these gainers and do a correlation on that and sort of a more of an in-depth analysis to see. And you can actually, based on that, you may be able to identify the sections that are G655, for instance, versus those that are G652.
Okay. Next question is PM due to ovality of core or core plus the cladding? Well,
if you think about glass, it's made like I use the term it's made like the rings of a tree. So when the glass is made, it's made in like on a lathe. And so everything is pretty distributed evenly. So, I don't have any hard data to this, but if you think about if I've got something that's slightly oval, and the only difference that I have between my core and my cladding is the change in refractive index when I'm building it, things are going to be pretty uniform all the way through the glass. So generally, if I have an ovality in the core, I'm going to have ovality in the cladding as well.
Okay, and you did bring up before the age of the fiber is important because the tolerances have improved substantially over the years, and so for those that have older fibers, then you can expect worse measurements than you would with the newer installations. Another question, is PDL a measurement of PMD?
PDL is polarization-dependent loss, and generally you only worry about PDL or polarization-dependent loss when you're dealing with optical components. When I used to work for Agilent Technologies, we actually had a polarization-dependent loss tester. We had a PDL tester that would actually measure the polarization-dependent loss, which is a loss contributor. It's an attenuation contributor based on the polarization itself. So I would say it's not a major contributor. You could have polarization-dependent loss, but it's more going to affect the attenuation, not the polarization mode dispersion.
Okay, another question is an example, and this is for a 10 gigabit per second route in a metro area using a G.652 fiber for a span of less than 10 miles. Would you expect a failed CD and PMD test?
Over 10 miles, no, I wouldn't expect that. I mean, generally, as a general rule with G.652 fiber, you would be able to go, if you do the math with you use your 16.5 or average picoseconds per nanometer dot kilometer, and you know that at 10 gigabits per second, assuming we're talking about SONET or SDH, okay, you're going to have a limit of CD of about 1,000 picoseconds per nanometer. And that's going to translate into about a range, a typical range of about 60 kilometers that you could go with that 10 gigabit per second signal. Now, if it's 10 gigabit Ethernet, the number, remember the number is not 1,000, it's more like 740, 730, 738 is the number that I think the standard refers to. But so you just do your math. You take your coefficient that you test and you multiply it times the distance, or you can take your limit and divide by the coefficient, and you can see what the distance range would be on that fiber.
Okay, thank you. For another question, do you recommend 100% testing on the fiber in a cable in terms of CD and PMD measurements?
Well, again, that's difficult to say. I mean, if it were new fiber going in, I would probably recommend a baseline of all fibers that are going in. Sometimes you're only dealing with 2 fibers at a time. I mean, I deal with companies all the time. They're going out as they roll those fibers in, or as they turn these fibers up, they're doing the testing at that time. So it's not necessarily the case that everyone baselines every single fiber in the cable. I mean, as an ideal situation, you might want to do that, but in reality, or in the world I see today, I don't see that often that companies are coming in and doing it the whole time. I would recommend, though, you would do it if you're leasing fibers, or you were purchasing. If you just purchased a company, for instance, and you bought their fiber infrastructure. If it were me, I have a contract that means they sold me whatever they sold me. I would actually want to go in and baseline all that fiber and see exactly what I'm working with. I want to see the performance of that fiber because I didn't do it myself, and I don't know what necessarily is in the ground. Just because someone agrees to lease you or to sell you a G652 fiber, and that's what they tell you that you have, doesn't mean that's what it is. And I have examples, I have real-life examples in the field with clients that they thought they had G652, and they went ahead and bought components. They bought dispersion compensators based on that, and after we tested it later, we found out that it was perhaps a mix of G652 and G655. Again, it's a good practice to test this stuff to validate what you really have, so you can plan better, so you can engineer more accurately, and you're not having to redo things after you find out the hard way.
Okay. Another question is, what industry standards are referenced for CD and PMD testing for 10 gigabit Ethernet?
I don't have the reference numbers off the top of my head. I'm terrible with memory in terms of what the actual numbers are. But if you, what I could do is get back to this person on the exact numbers. Some people have them off the top of their head. I personally don't. But we can definitely get those reference numbers to you by email if you want to leave your information, or you can actually contact me directly off the slides, or contact Larry, either one, off the information from the slide sets, and I'll be glad to provide that information to you. I'm not prepared to go into that kind of detail here.
Okay. What type of time frame are we talking about? The question's kind of convoluted, but how long does it take to perform a CD test or a PMD test?
Well, I can do a full scale. I mean, we're doing this in class today. I can do a full, I use my test method depends on how many fibers I need to test. I'm getting ready to do some testing actually in Asia here coming up, and I'm going to be testing a fair number of fibers for a private network owner. And I'm going to need as efficient of a system as I have. And by using, for instance, in this case, it's the Viavi auto bidirectional. They've got a full bidirectional deal where they have everything in like a couple of boxes, and you have a switch in there, and you've got automation scripts and everything else. And once I get that set up and ready to go, I can perform IL, ORL, OTDR, CD, and PMD in under 5 minutes each fiber. So I can actually perform that. If you're just testing CD and you're performing a test, once you do the referencing, it takes the actual test itself, once you hit the start button and you get the result, takes about 20 seconds. PMD is around the same time. It takes about 15 or 20 seconds to run. Using those methods that I mentioned earlier, it takes about that much to run the test once you're hooked up and ready to go on each of those tests. So doing a full-scale test of the whole spread of tests, once you're lined up and if it's automated, that actually you can do it really quickly. So it's a matter of efficiency. It's a matter of how many fibers you need to test on a given day. If you're just doing a couple of fibers, you probably don't need to automate it, right? You just need to go in and test them individually and run those tests. But some methods take longer than others, and I'm only referring to the phase shift method for CD in this case would take about 15 or 20 seconds. And that's covering the SC and the L band.
And I believe this question has to deal with environmental things, but when to get the worst case measurements, and I'm thinking that may be caused by temperature variations due to weather conditions.
Well, again, we're talking PMD here. So again, recommended is if you just take a PMD shot one time, it's the PMD value at that moment in time. So if you were to turn around and make that measurement a few seconds later, let's say I even flipped my test cord over. If I flipped it 180 degrees over on the table, I'll get a little bit different measurement. So when we talk about extremes, this is talking about what is the PMD value on a nice sunny day? What's the PMD value on a windy day? If you've got an aerial plant, what's the PMD value when it's the coldest day of the year? So you could actually pick those times and actually look at the values and create sort of a plus minus. And so you're basically just looking at the PMD distribution. You're looking at what varies, and it'll probably fall, I think it's within plus or minus 10 or 20%, the numbers that you'll get. I mean, it's not going to vary hugely or in a huge way, but it will vary a bit over different conditions. It'll even vary a bit over very similar conditions, but not as much. It should vary a little bit more under extreme conditions. There's no magical formula for this. It's just a matter of making sure that you're taking representative shots over the kind of weather that your fiber is going to experience over time.
Okay, another question is on ROADMs. If during doing TMD and CD testing where the span has ROADMs, reconfigurable optical add-drop multiplexing, do you have any input on that topic?
Yeah, it's a lot more complicated. When you get into ROADMs, you're dealing with wavelengths that are being dropped and added and moved around and everything. So it's a lot more complicated. I'm not ready to get into that today. Matter of fact, it's really difficult as how you would do it in a given situation. In mesh networks, the best way to do, keep in mind in mesh networks where you're using ROADMs, you can have all kinds of different routes. So what are you going to do? Test every single possible route that you're going to have between point A and point B? The combinations could be endless, theoretically speaking. So one approach would be to test each span between ROADMs. So if you could test the sections between each ROADM, you have the data for each of those spans, and then you could calculate through different ROADM or different mesh network combination of paths, you could actually calculate what your CD or PMD would be through those different paths. That's what I would recommend people do because the added complexity with dealing with ROADMs is a bit challenging.
Okay. Tim, in the first fiber characterization session, we were recommending that test as far as optical loss testing, OTDR, and optical return lossing loss testing be performed. We still, I want to just get your thoughts on this. This is a personal question from, saying you need your baseline measurements or your basic test practices, and then we go to the enhanced enough. But out of the three, is there one that stands out that's going to be more important at the higher speed?
IL-ORL or OTDR?
Yeah.
You're saying those three?
OLTS, OTDR, and ORL.
I would say they're equally important. I mean, if you think about an optical network, your insertion loss measurement is your baseline. That's like, you've got to know whether you're going to be within the link loss budget. That's a given. ORL isn't that critical on lower speed systems because lower speed systems can tolerate reflections better. But as you get to higher speed networks, ORL becomes much, much more critical. And I think it actually reaches a point where it's just as critical as the insertion loss measurements, but you can't not do an insertion loss measurement. You could choose not to do an ORL measurement. I could also choose to do the ORL measurement using my OTDR and not an ORL meter. So I could skip the ORL measurement in a purest sense. I could run my OTDR measurement and get ORL and reflectance data. Keep in mind that with an OTDR, you're able to get ORL values if you use launch and receive cables especially, or able to see, the point here is you're able to see, measure the loss and the reflectance of each distribution frame connector pair. So you can do that on an OTDR. So you could technically use the OTDR to do the loss ORL measurements, and technically you could use an OTDR to get a really good idea of your insertion loss values. So if I had to pick one of those three, I'd pick the OTDR because I really need that visual view of the fiber network overall. And if I only had one of those tools, I would definitely pick the OTDR because I can get IL results out of it, I can get ORL results out of it, and I can get all the other OTDR benefits for it, keeping in mind that my ORL and my IL values will not be as accurate using the OTDR as it will if you use an insertion loss measurement, a traditional insertion loss measurement, and a traditional ORL measurement.
Okay, we have one last question here. How would you identify the location of a section of fiber that fails PMD within a span of the cable?
I would use as a section of PMD.
A section of fiber that fails PMD within the span.
That fails PMD. With the methods that I'm talking about, you wouldn't be able to determine the loss per section. I think Expo actually has a device supposedly that will provide sectional assessments of PMD. I've never used those devices, but I understand that they do have those. So I wouldn't really be able to speak intelligently on that topic to that level. You would need to probably get in touch with them on that. But the values that we're talking about here using the methods we talked about today will do span PMD values, and it'll give you numbers for that entire span, but it will not break out those sections section to section. And I'm not sure if there are any other manufacturers other than Expo that actually offer this sectional value measurement.
Excellent. Let's go ahead and advance to the last slide here, and I'll give my closing comments. Light Brigade and Fiber Insight would like to thank Lightwave and Pinwell Corporation, but we also want to thank all the attendees who took time worldwide to schedule to participate in this session. We will be sending the information to you within a certain time frame. I'm not sure whether it's 12 hours or 24 hours, but anyway, within the day, you'll have access to the slides. Also that the webinar is also archived with lightwaveonline.com. So for those who weren't able to participate or missed a portion of it, you can watch it at a later time. And so from the Light Brigade and Fiber Insight, we want to thank you, and we hope to see many of you at the upcoming Optical Fiber Conference in March in Los Angeles. Okay, so take care and have a great day.
Thanks, everyone. I got to wrap up with these guys for just a minute, and I'll be ready to rock.